In the next video, I wanted to talk about what happens when we have irrational zeros and where do we go from there. And also complex zeros. Kind of in a couple videos ago, I started to talk about what happens, when we run into square root of negative numbers. Where do we go from there? Because those sorts of ideas are important for within our last few polynomial theorems, besides this one. So let's say we're looking at p of x is equal to this polynomial here. And again, the point of the rational zeros theorem as I see it is that when I'm looking at a polynomial, I can instantly determine what my possible rational zeros are. Because I see there is no leading coefficient, meaning there can't be fractions. And 10 is my constant coefficient, meaning it's got to either be 1, 2, 5, or 10. So there's not that many options here when it comes to rational zeros. And I could, what I would always recommend is starting with the graph of the polynomial, because that will definitely help me understand its behavior and how those intercepts look without doing anything else. So let me go ahead and type this bad boy in. Plus 23x plus 10, and we will see what we're working with. Okay, let me increase my X window a little bit to say 6. And what I notice is it appears to cross the x-axis 4 times. It looks like this one's at -2. That one is looking like a strong possibility to me because 2 is a factor of 10. This one, it appears as though, well, maybe this is somewhere between 0 and -1. So you might hypothesize maybe this crosses at -1/2. But to me, this would be a red flag, because since there is no leading coefficient, I know 1/2 cannot possibly be an answer. So the next question is, let me make this a little bit bigger once again, what is the 0? If it's not possibly rational, that implies that this must be irrational. And the question you might wonder is, well, what do I do? Well, we'll see in just a second. Looking at the next ones, it appears as this one's at 1, 2, 3, 4, 5. This one over here, 5 is a possibility by the rational zeros theorem, since it's divisible, since 5 is a factor of 10. And this one looks like it's somewhere between 2 and 3. But 2.5 or 5/2 or something like that, that is not a possibility, again, because there is no leading coefficient. So what I'm kind of thinking right now is that perhaps -2, perhaps 5, perhaps those are zeros. The other two, I have no flippin' idea. But what we could do is use the zeros that we think work first and see where that leads us. So let's go ahead and use synthetic division to begin factoring p of x. So we have 1, -5, -5, 23, and 10. And we are dividing by the two zeros that I think are rational, which are 5 and -2. So let's just start with 5. And 1 times 5 is 5. This would give me 0. 0 times 5 is 0, plus -5. Multiply, -25, add, -2, multiply, -10, 0. And what I can confirm is that x minus 5 is a factor of this polynomial. And the quotient is going to be x cubed minus 5x minus 2. And also I could check -2, which appeared to be rational 0 as well. Let's see if it works. Yes, it does. Cool. And so I know that x plus 2 is a factor of x cubed minus 5x minus 2. And what I would be left with is x squared minus 2x minus 1. But notice that as I factor out the rational zeros, what I'm doing is I'm making my polynomial simpler. And once I get down to the point of being a quadratic, we know the quadratic has a solved solution because of the quadratic formula. The quadratic formula always gives us the 0 to any quadratic as well. And there exists such a formula for cubic and quartic polynomials as well. We did not talk about that in class because we didn't have time, but those formulas are quite a great deal more complicated, and I would never expect you to know those. And ultimately, a lot of the stuff that we're talking about in this chapter kind of invalidates the need for those in the first place. I mean, not entirely, but as with more theorems, you'll see what I mean. But in this particular case, basically, this polynomial is where we might get stuck. And if you tried to factor this using a traditional magic X method or something like that, you will see that this polynomial is prime. It can't be done. It can't be factored using rational numbers, at least. But if we apply the quadratic formula, we would get 2 plus or minus the square root of b squared minus 4ac all over 2a. So that, actually, let me go ahead and I want to move this. Dang it, I clicked something wrong on my tablet. Now it's all out of whack. I wanted to move this up. I think I can move it without having to rewrite it. No, that's not what I wanted to do. Well, shucks. Whatever. I'll just go ahead and leave it here. But what I would be left with is 2 plus or minus the square root of 8 over 2. And the square root of 8 simplifies because it's 4 times 2. The square root of 4 is 2, which would give me 2 plus or minus 2 root 2 over 2. And if I then notice that there's a common factor of 2 in each of these, well, 2 divided by 2 is 1, and 2 root 2 divided by 2 is just root 2. But basically, the quadratic formula will tell me what are the zeros of this polynomial. And what we can see is that they are irrational. In this case, they involve the square root of something which is not a perfect square, root 8 in this case. We can simplify it, but what we get is a zero that's kind of an awkward zero, or again, what we call that is an irrational number, right? Any number like the square root of 2, pi, e, and the likes are irrational because there's no simple decimal explanation. It's an infinite string of digits which never end. And we can use a calculator to try to understand what those are approximately. But ultimately, it's not rational. And that's why these obviously will not show up on our list in the rational zeros theorem. It doesn't mean I can't find them, but to sort of summarize how we can think about this, the rational zeros theorem helps us find the easy zeros. Then if we want to find the ones which aren't so easy, we can always resort to things like the quadratic formula, because the quadratic formula allows us to find out the weirder zeros, ones which might be irrational, and so on. And last but not least, let's look at what those look like if we wanted to say, well, what is 1 plus root 2 and what is 1 minus root 2? And let's just check to make sure that this actually all makes sense, because those two zeros are approximately 2.41 and negative 0.41. And if we go back to our graph that we had before, notice that those locations, right, if I calculate the value of those zeros right here, I can actually figure out what those are. And notice my calculator will give me, well, this zero occurred at 2.41421. And that's exactly 1 plus rad 2. So my point is, sometimes when I'm trying to figure out the zeros of a polynomial, sometimes they're weird or ugly, and they're going to be weird irrational numbers. But we can use the quadratic formula in conjunction with synthetic division to figure out what those are exactly. Again, an exactness is sometimes important. And over here, what we'll see is that is 1 minus root 2, aka negative 0.4, if we were to actually go check it.